answer. Title is the probing color is of QCD, but from spin transformation in heavy operations. Please.
Okay, thank you very much. Yeah, it's always my pleasure to visit Kyoto. So I think this is the second time of my visit after COVID. Yeah, visit 2003. Yeah, at that time, yeah, Yoshimasa was still not here, and it's unfortunate and very sad farewells to Onishi-san. Okay, so anyway, that's at the beginning. I want to share some memories about YITPs. So actually, in 2019, I and Yoshimasa and Koichi Hattori organizes this molecular workshop of the quantum kinetic theories in magnetic and optical fields. And at that time, I think I was at the KO and Yoshimasa was still at the KK. And which is actually he's local. At that time, he was at the Chicago. Yeah, so we have.
At that time, I was.
He's still in Riken. Okay, so it's even before you move to KK. So there are many familiar faces here. I guess you guys know some people here, like Igor Shokobi and Nasa, Kenji, Shuba, etc. Yeah. So at that time, I mean, basically the purpose to have these workshops is to gather the experts to discuss how we could develop this kind of quantum kinetic theories, basically for spin transform, understand dynamical spin polarizations and quarks. And it turns out after 5 years that this journey still continues. And today I will just tell you some update about progress and then how we can really apply this kind of theoretical framework to start spin transforming heavy conditions. So this is the outlines of my talk. So I will begin with brief introductions to the spin polarization, spin alignments, phenomena, the applications. Then I will briefly introduce this quantum kinetic theory for spin transports, especially for quarks under the background fields, certain with field approximations. Then I will show you how we could estimate the spin alignment spectrums for these 5 methods from the glasma effects in heavier conditions. Use framework. And if I still have time, I guess I will have. I will also mention how we study like the quarkonian transposes, or actually we derive this kind of quarkonian transpose equations, polarizations, from a different approaches that is called combinations of effective field series. And make the summaries out. The talks will contain some technical part, but due to the time constraint, I will not explain everything, so I will just highlight some important steps of these mathematical formulas, but details later or even during. Yeah. So as the beginnings, let's have this kind of pedagogical introductions is that in heavy ion conditions, especially in the peripheral conditions, these two gliding nuclei along the bin directions carries a large angular momentums, and it is believed that this kind of a large angular momentums after the collisions can be converted to the so-called kinetic vorticities of the quark plasma because the rotations of quark plasma, and this will give you some kind of vertical fields. And from the some numerical simulations, they can simulate this kind of magnitudes of vertical fields and evolve with respect to time with the different collisions energies. Interestingly, that in fact the maximum of these vertical fields actually exists for relatively low energy collisions. So the reason is basically there exists some competition between the non-relativistic and the relativistic effects. So if you really have a very high energy collisions, it turns out that these two nuclei just pass each other. So the positions of this total angular momentum is the quark plasma is not sufficient. In fact, in the nuclear stopping effects, you have the larger angular momentum for the reference. That's why actually the lower energy collisions instead larger vorticities. But basically, these vorticities is also related to the impact parameter, so you need more peripheral collisions to generate stronger vorticity. The magnitude of these vorticities is actually quite strong compared to the other physical systems, although the sizes of this vortical field is also very small, subatomic scales. That's why it's called subatomic swarms. Then the question is, of course, that how we can prove this kind of vorticities from some experimental observables. So it was proposed long time ago by Di-Lun Yang and Xin Wang that one may possibly measure this kind of global polarizations of lambda hyperons. Actually, not sorry, maybe not really from the series, but actually from pollutions. Experimentalists proposed this idea, but Zhou and Xin they just proposed that this kind of large orbital angular momentums can be converted to the spin polarizations and spin orbit interactions can be regarded as kind of a bonus, a relativistic Barnett effect. And then in experiment, this kind of polarizations can be measured through this weak decays of lambda hyperons. Because in such a process, the spin polarizations of lambda will be preferably parallels to the momentum directions of the protons. One can track the polarization spectrum. And also from the quark model, basically the lambda spin is just governed by the spins of strange quarks therein. So if you can polarize the strange quarks as quark plasma, then the polarization can be very close to polarizations of lambda. And this is the experimental data for lambda anti-lambda bar polarization. Lambda bar polarization with respect to the collision energies, and indeed at the lower energy collisions, you see the increases polarization is expected. And on the theoretical side, to have a more accurate descriptions for these polarizations, it was found that if you assume the global equilibrium conditions, then these polarizations spectrums can be described by this so-called modified Cooper-Frye formula, which is basically just governed by this quantity called thermal vorticity, where the beta is just the fluid velocity over the temperature, okay, and this distribution function is and if you have a small temperature gradient, then these terms will be mostly given by the kinetic vorticity, as I just showed you previously, and you can compare the and actually this modified Cooper-Frye formulas lead to a very good agreement with the so-called global polarizations. Okay, extract the vorticity from this measurement, and actually matches what we expected from the previous relations. So now we have this very vertical fluid in quark plasmas. Okay, but this is not the whole story for the spin-related observables. So it turns out that we have another spin-related observables, which is called the spin alignments of vector metal. So this is a bit different from the polarizations of lambda hyperons. So how to measure these observables? So basically, let's take the 5 mesons, which comes from the SS bars examples. So basically, people study these spectrums of the decays of particles like the kaons with the angular dependencies with respect to this n hat, which is called the spin condensation axis. This spin condensation axis is chosen in experiments. In heavy ion collisions, it's chosen to be perpendicular to the reactive plane, okay, because this is the total angular momentum direction, called y direction. And basically, if you study this zeta star dependence, you can extract this low zero zeros, which is called the zero zeros components of the spin density matrix. And this is the quantity to quantify this kind of spin alignments. The point is that from the coalescence, quark coalescence model, most of low energies like mesons come from the coalescence of antiquarks. Then this low 00 is in connections to the spin correlation of the quarks and antiquarks along this spin correlation axis. Okay, then you can see if these values deviate from 1/3, it basically implies that there exists a non-zero spin correlation. Okay.
Excuse me, so in general, correlation function is always finite, usually. Because that is a two-point function. So,
yeah.
So in that case, I wonder, rho 00 is always
right. So in fact, to be more precise, this is a kind of an old formulation. In fact, not only to have the correlation, you need to have an isotropy of if these correlations are isotropic along all directions, then you will not see the spin. These low 00s will be still one, just once. Yes, that is important. So you need an isotropy of these correlations.
So in this calculation, the expectation value is the isotropic one, or
in their very early expectation, they just assume we only have the correlation along the y direction. So and that is just a very early proposal. Later there exists more rigorous expression of this low 00 in terms of correlation, spin correlation. And if you take spin correlations isotropy, then you will get just one. Then you need the isotropy. Yeah, that's important. Yes. Right. So in 2020s, the Alice collaborations in LGC first measures these spin alignments for K star 0 and the phi mesons. So just look at these red dots, especially at the lower transverse momentous regions. And later also the star collaboration in RICH is a low energy collisions. They measure the so-called global spin alignments, which means they actually integrate over the certain PD ranges of these low 00s, and then plot this with different collision energies. So for phi mesons, they actually observe the low 00 increase with the lower collision energies greater than 1/3, but there exists no substantial net spin alignments for K stars. Yeah, so actually they have somewhat different results. But theoretically, basically this leads to a kind of a puzzle because for either cases, the deviations of this low 00 from 1/3 is unexpectedly large. So if you just consider the polarizations of a single quark from the vorticity, this correlation is second order effects for omega over t, that is extremely small, especially LGC energy. So you need other mechanisms in principles to generate this kind of non-zero spin correlations. And of course, we also have a very complicated collision energy dependencies and the flavor dependencies for these low 00s from the Alice and star data. So they even have the different sign for low 00 minus 1/3. And later, Alice collaboration further measure the spin alignment for jet psi, which also show low 00 smaller than 1/3 at the low PD regions. And for jet psi, it's even heavier, so you don't expect that it can be that by this vorticity. So, yeah.
So Alice and star has a different direction. Deviation. I mean, the rho 00 is smaller.
Different. Yes. Yeah. Already collision energy dependence is there. So with So yeah, it depends on different collision energies.
It's a different.
Yeah. This is star is 200 GeV, and also below 200 GeV, you see greater spin alignment for low 00 greater than 1/3. But Alice is at the 2.76 TeV, so that's much higher energy. So the scenarios are actually also different. I will later explain the possible combination. And so what are the other mechanisms from electromagnetic electromagnetism? We know charged particles may be polarized by electromagnetic fields, like this kind of magnetizations for the polarization of low magnetic field, or spin Hall effect that can generate the transverse polarization perpendicular to electric fields and momentums. But now, how about the situation if we have some gluon fields in the QCD matters? Actually, what we want to have is more like a kind of chromo-electromagnetic fields. Can we really generate such a kind of fields in nuclear conditions? So before talking about the situations in heavy ion conditions, in fact, even in the deep inelastic scatterings, this kind of very small collision systems that could be possible to realize. The point is that, okay, in deep inelastic scatterings collisions, if you consider the small Bjorken axis region, this Bjorken X basically characterizes how much the momentums of this scatter patterns is inherited from the mother photons. And basically at the small X regions, one can see this is the pattern distribution functions of the up-down quarks and the gluons, and you see the rise is gluon distribution function, the small X. And the scenario is actually, the schematic scenario is actually that small X regions, this pattern sizes inside these nucleons may be expanded, and that becomes more and more blurs, and that actually get saturated in the target. Okay. So in some senses, you will have this kind of distributions of this oversaturated gluons, especially gluons, yeah, which like is a kind of a condensate. So they becomes this condensated. The low energy regions is smaller than these so-called saturation scales, QS. And this QS actually also depends on the sizes like these targets. So the important point is that when you have this kind of saturated gluons, in fact, one can describe their dynamics through the classical Yang equations. So they can be characterized by some kind of classical chromo-electromagnetic fields. Okay. And this is the so-called color-glass-condensate effective series for this saturated gluons proposed by Macaronis and Gopolos. So basically, the picture is that these fast partons, some quarks inside these nucleons, provides the source of this kind of chromo fields. So these chromo fields are described by the Yang equations for the non-abelians electromagnetic fields, and there you see the source coming from the particles. And why is it called color-glass-condensate? So color basically easy to understand because gluons carry color. The glass is because of the disorder, because inside these protons, this color charge actually fluctuates in space. You have this kind of disorder, and also the fluctuation time is relatively slow compared to this accretion times. So anyway, so that's the reason because of this disordering and the slow variance fields, it's called the glass. And we have a saturations, and that's why it's called condensate. And now in heavy ion conditions, you have actually two sources. Both nuclei can serve as the source for this kind of color field. So the scenario is that you will have longitudinally dominant is a chromo-electromagnetic field. Longitudinal means longer field. Okay, and this is kind of the simulations for this kind of chromo fields. So basically, they are very strong at the early time, but they will decay time. And also because they are fluctuating, so here what they simulated is actually the magnitude instead. just one field. Yeah, and then the saturation scale here, it's actually relatively large compared to the QGP temperature, so it can reach 1 to 2 G, much larger than the QCD temperature, like 300 volts. So before we try to use this kind of glasma features to explain this spin alignments, let's just review some essential ingredients for spin alignments. So in the very beginnings, when the spin alignment was measured, people were slightly confused because we have a small lambda spin polarizations, but large spin alignment. It turns out that the spin correlations is not really the same as just the product spin polarizations is quark and spin polarization antiquark. So basically, you could have the large spin correlation with small one-point functions of this spin polarization. And that means that basically this source spin alignment should be fluctuating, right? So it does not really affect spin polarization. Okay. And the second point is like just what I mentioned that it turns out that this sorry, actually the third point. Sorry.
Does it mean that if we could measure the correlation of spin polarization, that should be large because of that large fluctuation? So 1 point function is small because of their chance.
Yeah, but it's a little bit tricky, I think, because it depends on the distance. In principle, if you separate this lambda and lambda bars larger, the correlations should be weaker.
I see.
And but for the coalescence, they basically collide at one point, mainly to the kind of intensity. So it's a tricky issue. So spin correlation is basically very small, yeah, because it's more or less like the products.
Almost
unless they are very close. Yeah. So yeah. So the second point is actually this low 0, 0 is normalized. Low 0, 0 divided by low 0, 0 plus. So the spin condensation actually anyway need not be always parallel to the spin polarization action. And the anisotropic spin correlation is needed, as you said. If you have just the isotropic correlation, still get those 0, 0 once. So based on these ingredients, that's why we think this glasma fields is maybe a potential source to give us these non-trivial spin alignments. Because first of all, it has these intrinsic scales, saturation scales for these chromo fields that is much larger than vorticity. So that's the possibility to generate a strong spin correlation. Also, these fields are fluctuating, okay? So which means it's not that possible, not quite possible for these kind of chromo fields to affect the spin polarization, especially for the global spin. Thirdly, it has the intrinsic anisotropy because as I mentioned, these chromo fields are longitudinally dominant at early time. So we basically have three nice features of this glasma field. So what we propose is that if in the glasma phase that exists in the early stages of heavy ion conditions, I don't know. I'm not sure the students are very familiar with heavy ion conditions. And I assume they know this area. So basically, you have an early time with the glasma phase, and then later you will reach thermal equilibrium, become the quark-gluon plasmas, and become hadronic phase. Yeah. So that's just assume that in the early time, we have the quark and antiquarks created in this glasma. Okay. And the glasma fields is polarized spin, these quarks and antiquarks. Okay. Then later they will also go through the quark-gluon plasma. Due to the scattering effects, this will lead to spin relaxation. But as long as this relaxation effect has not completed, wash out the initial polarizations, when they recombine, then this spin correlations is encoded in the low 0, 0 for fine mesons can be led by the correlations of these initial chromo-electromagnetic fields. That's the idea. And so how to study this? Then we have to track the spin evolutions of this quark, and that was from glasma phase to QCD phase. Then we have hybridization. So what we apply is this quantum kinetic series for Wigner functions to study the dynamical spin evolutions of these quarks. And then later we use the coalescence models to relate their Wigner function basically.
I want to understand one thing. So spin alignment, I mean the spin quantization axis, where is which one? Is it?
Yeah. Now in heavy ions, it's still chosen to be perpendicular to the reaction.
Right.
But it need not be like that. You can choose arbitrary.
Yeah.
It's based on experiment. So it will also depend on the choice. So in experiment, if you choose a different thread, then you measure.
I do not understand actually why this effect gives rise to spin alignment. So you mean plasma field is random. Then then it produces random spin. How to say ensemble or alignment.
Yes, that's right. So then it does not affect the spin polarization like the lambda polarization, because it comes from the polarization of a single quark, single strength quark. But spin alignments come from spin correlation, the quark anti. So if you consider that's the important one. So you consider the correlations of this chromo field, then it's not zero. If it's not a correlation, it's just the expectation value of a single field, then so that's why we think it's reasonable, because it can give you larger correlation, but just very small 1 point functions. So it does not affect lambda, because lambda polarization, at least for global lambda polarization, has been already successfully described by participants. You have extra effects, you will just lead to some deviation. That's why I believe this is possible. And yeah, I will quickly go through this since it's really relatively technical. Yeah, so anyway, but so what we want to consider for the polarization spectrums now in the more general cases, can be basically described by the ratios of these actual Wigner functions to the vector Wigner functions. And why do we have this kind of decomposition? Because it's basically this vector Wigner function just if current energy momentum tensor characterizes the charge energy momentum transfer. But the actual ones is related to the spin, because if you integrate over the momentum, the energy or even the full momentum space, you get the actual charge current. And if you just think about the message particle, the chirality is just holistic. It's easy to understand that actual current is kind of okay. So the point is actually that we have to track these A mu's for the quark and also anti. And then let's forget about this power counting, but basically this A mu, the V mu, that contains some of the variables that describe basically the charge distribution and the spin distributions in the phase space, which is given by this FV. We call it the vector charge distribution function. And these equations to track the phase space evolutions of FV is the standard Boltzmann equation, basically Vlasov equation when you do the electromagnetic fields. Okay, so here I just first consider the cases for just usual electromagnetic charge particles. I don't introduce color just for simplicity. So this can be regarded as, for example, electrons. Okay, and of course you have the collision terms. But then if you want to track the spin polarizations, then you need to know this kind of spin distribution as a kind of pseudo vectors in the phase space, right? So you have this additional actual kinetic equations, okay? And the important point is that it has now the entanglement with respect to also this vector charge distribution function. So if you have some inhomogeneities of the charge distribution, then you can actually dynamically generate spin polarizations. Here, this is even more complicated. Collisional effects is that include the spin orbit interactions, and that's the reason why somehow if you have a non-equilibrium system, then if the spin finally reach equilibrium, then it can be given by this contributions. Anyway, but today we will mostly focus on this the background fields contribution, especially when you have this dynamical, if you have this space-time dependence of the background fields characterized by these field strengths, then these terms will serve as a source term that dynamically generate polarizations. And also for the full actual Wiggin except for this A to the mu solved from these equations, one actually have this this contribution also come from the electromagnetic fields, and this term is more explicitly related to the magnetization and the spin Hall effects as I just mentioned previously. Physics. But this is just non-dynamical effect because these fields are only at the final spin freeze-out time. But this solved from the kinetic equations can carry the memory effect. It's from the kinetic equation, track the full evolution, so it can tell you even the early time. This term will be actually more important for our purposes to study this plasma. So, but anyway, if you're able to solve this and then plug this into here, then in the end, you just can calculate the spin polarization spectrons is for the single quark. The data, of course, you will take the correlations of this single quark polarization and other anti-quark polarization. I guess this will be too technical, but so let me just quickly go through this. So for the color cases, for the quark, it's however more subtle. You have to actually decompose all this distribution function into the color singlet, the color object. And but actually in the if you take the weak fields approximations, the leading order contributions is for these spin correlations will come from the two color uptake components of this spin vectors, actual distribution function. So anyway, so that's why I will mostly just focus on the color uptake components. The point is that in the weak field approximation, that's assumed out in the glasma phase, there exists a color chromo-electromagnetic field here, surface the source term, and you can solve these kinetic equations to get the dynamical polarizations, which actually come from the difference between the initial chromo-magnetic fields at the TI and the later chromo-magnetic fields at the time, at the so-called thermalization times that it's at the end of the process. But at this moment, the glasma fields have already decayed. So you can actually drop this term, focus on this one. So from this dynamical contribution, you can actually have the early time contributions is from these chromo-electromagnetic fields. And then the quarks will enter the QGP phase, right? After this thermalization time. So when T is greater than thermalization time, you no longer have the glasma phase, okay? but then there will be scattering effects that lead to the spin relaxations. So we use basically the relaxation time approximations. Then this will give you these exponential factors that suppress the initial polarizations. Okay. So this T minus TTH is basically how long this quark travels through the quark plasma. Okay. So roughly speaking, if you combine everything together, your actual Wegener function is governed by two contributions. One is the spin polarizations coming from the initial chromo-magnetic and the chromo-electric field. Right? So this form is very similar to the magnetizations and the spin Hall effects, but these are related to the early time fields, not the late time. Late time fields zeros. So this is a dynamically generated, and then you also have these factors characterize the spin relaxation. So if this relaxation time is small, and the quarks, antiquarks travel also very long in quark plasma, these suppressions may wash out the issues. Now, the point is that, okay, as you also mentioned, right? I mean, if you really take the expectation value of a single Wegener function, then that's the expectation value of a single color field, then it vanishes. But for the coalescence models, now this low 0, 0 is actually related to the correlations of the actual Wegener function for quark and actual Wegener function for antiquarks. So you actually have the correlations of the two fields. So basically, so schematically, I didn't show the exact equation, but schematically, now this low 0, 0 or low 0, 0 minus 1/3 is basically governed by the correlations of two chromo fields. Could be two chromo-magnetic field or two chromo-electric fields. And here you have this spin relaxation effects. Okay. I have two here. One comes from quark, one comes from two. Okay, so that's basically the formula. To make some numerical estimate, then we have to just input some numerical values for this, for example, for these chromo fields correlators. Okay, but I didn't show the details, so you can use some GPWs. Anyway, some kind of models to calculate this kind of correlation function. Okay, and of course there are also some other assumptions we can discuss that later. But basically, by collecting all these input parameters, we can derive the spectrons of these low 0, 0s for phi mesons. Let's take phi mesons as an example. Okay, so this is the plot that I show this now. These low 0, 0s coming from this kind of glasma effects with somewhat with the transverse momentums of the vector mesons dependence. Okay. So that's first. So here the red curve and the blue curve correspond to the zero rapidity and the forward rapidity. Okay. And let's firstly take a look of the solid curve. Okay. So solid curve now correspond to the situation where you have no anisotropy of the transverse momentums of this vector mesons. So now, because we are considering the moving vector mesons, right? It has a momentum dependence. Yeah. So in fact, this those 0, 0 value also depends on their directions. So in fact, in this case, this is more like the you can regard it as more like a kind of central collisions, so that you don't generate an anisotropic flow. And the velocity of this vector mesons will be mostly isotropic in some sense. But of course, to be more realistic, you have to weight this kind of quantities with the particle spectrum. but basically schematically, this is the situation of central. And then you can see now, because of the glasma effect, this will lead to the low zero zeros is smaller than 1/3, okay? And then you will gradually increase and saturate that 1/3 with larger momentum. So
what was YQ?
YQ, this is the momentum repeated.
Rapidity.
Yeah. So different momentum repeatedly. Okay. Right. So in some sense, I mean, qualitatively, this somewhat matches this trend of the mesons measures. At least, but of course, you have to really weight this spectrums for better comparison, because actually there exists another situation. If you consider the more peripheral collisions, okay, then you have basically the dominant velocities of these vector mesons along the x direction. Y is the direction Y is the direction is okay? You have a larger flow. And it turns out that there will be a competition between the intrinsic longitudinal anisotropies from the color fields and certain momentum anisotropies of the vector mesons. Okay. So in the cases when you have this very strong flow, strong anisotropic flow, transverse flow, this low zero zero can even exist 1/3 the larger momentum regions. Of course, at the low momentum regions, everything is just dominated by the longitudinal chromo fields because there is no momentum difference, so you don't see the difference. But then at the larger momentum, then there will be certain competition between it could lead to the somewhat different behavior. So in principle, you have to really weight this with the particle spectrums with the flow to take into account the differences.
So excuse me. So how do you deal with the x and x prime on the red one? So do you assume a kind of a coalescence model?
Yeah, coalescence model, and in some sense they are very close. Yeah, so almost at the same point. So, but it depends on some details of the model. But they are almost at the same point.
You mean x and x prime are almost, but the particles are moving during the time evolution.
Yeah, but when they recombine.
Yeah, and then so yeah, quark and antiquark produced different place.
Yeah.
Somewhere and then combine.
Yeah. So it's little bit tricky. In some sense, yes, you're right. I mean, they are so they are really so in principle you have to track their initial position, but this will be too complicated. So in order to make some order of magnitudes, we did not really track their exact initial positions to the final positions for this field because otherwise it will be very complicated. But in reality, one should really formulate everything in a finite class. In our case, it's really like infinite class mass, and we don't have these details.
Okay. So anyway, you introduce some assumption to integrate out this x and x prime, and then you create mesons. But then, so distribution of this B is isotropic. It's isotropic.
It's anisotropic.
Then why this difference between By equal 0 case and Bx is 0 case? All right, it's
okay. This is very subtle because the point is we in a very original. Okay, if you derive this chromo fields. Okay. Also, firstly, that there exists some actually there exists some spatial differences coming from the momentum conservation, the coalescence. Yeah, and also what we do is that because this vector methods string alignment is actually obtained through the rest frame vector methods. So when we get these chromophile correlators, these chromophile correlators are the chromophile correlators, the rest frame vector method. But how to calculate these correlators, you have to do it in the left frame, right? So to do that, you have to boost these correlators in the rest frames to the left frame. Then the momentum dependencies will be involved, right? So in some sense, yeah, I can show you later, but basically because this boost, so then this will not be just, for example, busy here. It could be like busy plus the momentums cross easy. So then the momentums will be involved, and so then this will lead to the competition between the streams. Yeah. So it's, yeah, I skipped the technical part. Sorry.
I guess now you measure this 400 for the y-axis, I mean.
Yes.
Then if you change this axis to x, then behavior changes.
Right.
Okay.
That's right. So I will show you later. Yeah. But, okay. Let me finish. This is just a contour plot. It's consistent with this. I don't have to mention. And this case is just for completeness, but this is not a realistic situation because you don't generate the flows along the perpendicular direction. But then what I want to mention is that, okay, so now we try to use this glasma effect to probably to explain string alignments of fine mesons. But you see energy. You have low zero just on one side. For the high energy collisions, you could have this glasma in early time. But in low energy collisions, break after the top break energies, it's not possible to generate these don't have the small X ratio. So you need other source. And also, at the low energy collisions, what you get is low 0, greater than 1/3 instead of the smaller than 1/3. So what could be the other possible explanations? So here we actually propose some more exotic proposal. Originally, we proposed that okay, in the late times of the even in the QCD phase, there could be still this kind of chromophils. Okay, it may be like this chromophils, mostly transverse chromophils, induced by the Weibel type instabilities when you have the expansion, longitudinal expansions of the plasma. Okay, or even in a simpler case, you may regard certain soft thermal gluons as this kind of chromo-electromagnetic. And in a more, I will say, slightly more exotic setup proposed in these papers, they even propose that just before the coalescence, there exists some kind of a fine meson field, fluctuating fine meson fields, and that lead to like kind of chromo-electromagnetic fields to polarize the spin of quark. But this kind of fields is at the late time, just before the coalescence. So they don't have the memory effects. So actually, if you want to describe them, you just need to consider I call it the non-dynamical part. Again, this is like a magnetization and the spin Hall effect. But for the fields at the late time, just before. But the difference is that, okay, so forget about the turbulent cases. At least for this kind of fluctuating fine meson field or the thermal gluons, now they are isotropic because there's no reason to have this particular aspect. So then this will also lead to the different polarization spectrum. And in fact, this momentum dependence becomes important because now if they are the fine mesons at the rest, all these fields are anisotropic, as you say, and there will be no spin alignment. So you need the finite momentum of the spectral mesons to trigger this spin alignment. So you can see now in such a case, if you assume isotropic chromo-electromagnetic fields in late time, then you got a different results. Okay, so it's a complicated plot, but again, the different color correspond to the zero rapidity and the forward rapidity. But let's say if you consider the zero rapidity for the ray curves, okay, so dash curves correspond to the case when you have a large transverse flow, and this solid curve is the one without transverse flow. Okay, this one you can neglect. So you can see both this and this is at the zero, it's at the 1/3 without spin alignments, the zero momentum, because you need a finite momentum to generate the effect. So their alignments becomes substantial at the larger momentum region, but there is no spin alignments basically at the low PT regions. Of course, with the non-zero rapidity, you will, of course, have the momentum dependence, and that's why even at the zero QT, you still have the spin alignments. But basically, the point is that this kind of a momentum-induced spin alignments will give you low 0, greater than 1/3, mostly greater than 1/3, instead of smaller than 1/3. And these gentlemen, they use this fluctuating fine meson scenario and weight this with the particle spectrums, then they can successfully fit the data for reach with the Gaussian energy dependence. But this is fitting because although you have the qualitative trend of this, you don't know the magnitudes of this field. You cannot, especially for this fine meson field, you don't know how to calculate it. First principle. So they are just doing fitting. They assume there exists an isotropic fine meson field, and then they fit the data. But of course, it's not a trivial fit because you have just two parameters and you have to fit the different collision energies. It's still, it's not that trivial, but it's still kind of fitting, but they can describe the data at the reach. But certainly that's not the case for the high energy collision. In these scenarios, you don't really get the for this part, finally, let me just mention, as you said, you can choose different spin polarization axes. And so, for example, we can choose it along the bin directions. Why is that? Because in the bin direction is now uncorrelated with the reaction plane, right? So then you do not have this complicated transverse momentum direction dependence. So you only have a different rapidity dependence. Okay, so here I compare the cases from glasma and from isocoid isotropic color fields in QGP. Okay, and this is YQ equals 0, YQ equals 1, and you can see the sharp difference. Basically, glasmas lead to the dominant contributions low PT or low QT, but the QGP effect probably leads to the dominant contribution, large transverse. We hope the experimentalists further analyze this kind of data they can do. But of course, you have to also weight this with the particle spectrum. I don't have that. So I finished basically the part for this spin alignments for my mesons, mostly from the glasma effect. Okay. Any questions at this moment?
So let me confirm about the simulation details. So are you here? So choosing some initial state and also the QGP evolution from some specific some simulation code like code where you are here free dynamically solving all of the fields.
Okay, yeah, that's basically what one should do. So we don't have that kind of model. So what we do is everything analytic. But this depends on certain assumption, of course. For example, let me just quickly mention this. For example, this coalescence, okay, model, it depends on also several of the contributions. Like this correlation. These correlations, we can do it. We can calculate it by certain certain model. This is a GBW models for the dipole distribution color fields. So it basically gives you this kind of quantity. So this is more or less a kind of reasonable model. But there are other uncertainties like what about the initial quark distribution? Then we don't know. So we actually take the quasi-thermal forms by just replacing the temperatures with saturations. Unfortunately, we don't have much information on that. And also we have to consider the what's the QS. This is more or less like a reasonable numbers in glasma. Also take a constituent quark mass. But the biggest uncertainty is actually the relaxation times of this spin relaxation time. Because yeah, spin relaxation times, Yoshimasa, you know that in the collision term, the actual kinetic equation, the collision term is so complicated, it's not really in the relaxation form, relaxation time form, right? So there exists this ambiguity of how to define the relaxation time. So we just take some expressions from the heavy quark approximations in Ongos's and Misha's paper, and they just input some values. Interestingly, this gives you 5 points. So this is relatively long compared to the usual relaxation times charge. But if you consider that, and you also assume the quarks move like 5 Fermi long quark on plasma, that basically got they basically lead to the results. Yeah.
Is that the reason why the heavy quark is heavy?
What do you mean heavy quark is heavy?
So, can you show the? So the reaction time is proportional to the inverse of mass. Where?
Yeah.
Which means that if mass is large, then relaxation time becomes longer. Is it correct?
Yeah.
That's the reason why value is relatively large.
Yeah, but we also put just constituent quark mass.
You put
Yeah, 0.5 GeV there because it's strange. We cannot do much. So in some sense, it's kind of abuse of this expression. But the problem is that if you consider the relativistic quark, you cannot actually get the so-called relaxation.
You put the M square in a constraint quark.
Yes.
Oh, then.
There are lots of issues there,
Okay.
but because this is really the value we cannot really determine.
So how did you choose the constraint quark? How large?
We put it to 0.5 GeV. So roughly that's not a very bad approximation. Consider less than roughly the kind of classes. But yeah, this is unfortunately tricky. So
And the question was the initial distribution. What time is the initial condition time?
oh, we yeah, indeed, and we actually in our case we just push you to the initial times.
The initial time ground there is no.
Yes, that's right. Yeah, of course. That's then we know. Yeah, but yeah, in order to make the this approximation is similar. That's how we can directly calculate this correlation at a very early time and longitudinal fields still found. Otherwise, the transverse fields will increase. The analysis will become more complicated in that case. Although we have done some analysis in that case, but in terms of order of magnitude estimate, it doesn't change too much because there are also some other don't want to push it to put into 2D. Otherwise, it really requires. And the point is that if you just use, somehow you use this value anyway, coincidentally, it does not really lead to some large deviations compared to the scale. Somehow this roughly very close. 0.2. Anyway, but that's kind of.
So, what is the origin of this rapidity dependence?
Again, it's momentous. Momentum.
You don't assume boost invariant initial condition. For the car, let's say we don't. The point is that well, we just try to keep a general. So so this rapidity dependence is coming from the boost of these chromo fields, right? And that only relies on the momentum directions of this vector mesons. So if the vector mesons are produced at the large rapidity, this momentum dependencies will affect this. Okay, so your glasma is not boost invariant.
For the original correlations, it's boost invariant. But this momentum dependence just get into it after you just boosted the field. So it's not from the original field correlation. Correlation in the lab we do not consider this kind of rapidity dependencies of the color field. So the original correlation in the left front is independent of rapidity. But just because you boost it, and so the prefactor give you some rapidity. I have already spent 1 hour. Let me quickly go through this. Okay, anyway. Yeah, because I thought this is still something new relatively. You have already heard many parts of my previous talk last time. Although I have some update. So okay, so now the point is that you also see the spin alignment of the jet side. Okay. So that is more complicated because for this side is a quarkonia, which is formed by charm and anti-charm. It's more deeply bound. It's no longer like the 5 mesons that just come from the lessons of the free stretch and non-stretch. So to describe the dynamics of the quarkonia is more complicated. Actually, this is also the reason why it serves as a useful probe for the existence of quantum masses in the same size operations. Proposed by Matsuisa. Said that. The point is that in vacuum that you have Coulomb and the confinement linear part, but then in the finite temperature you have a screening, and there exists even this dynamical dissociations that come from basically the medium-induced scattering. So this will lead to the kind of jet size suppressions characterized by IA. This is basically the multiplicity dependence. And also, if you consider the high energy conditions at Alice, because actually they are then more this heavy quark and anti-heavy quark pairs is created. You don't even have the dissociation. You could also have the recombinations at a later time. And that's the reason why you actually get these saturations. That is a competition between recombination and the distribution, but not for the cases which not number of pairs. Okay. So now the question is, yeah, actually you could. There are many theoretical models, transport equations. So the question is that how you can derive this from the first principle. And especially for our cases, we are particularly interested in the cases of polarization. This has not been fully studied for the traditional quarkonia transport. Okay. So we basically use this open quantum systems and the effective field theory approach. Okay, so the reason we can use open quantum system is because the quarkonias or heavy quarks are dilute. Okay, QCD, and the QCD is the environment. These quarkonians can be regarded as system, and the Hamiltonian then can be decomposed into the system or subsystems, environment, and the interacting part. And the interacting part is assumed to be the weakly coupled. This can be realized due to these scale separations for the components, heavy quark. For example, you have the 1/n expression. So, and then to really realize this, to know these details, we have applied this certain effective field theory. Okay, QCD itself is complicated. So you basically integrate out the certain high energy degrees of freedom. For example, you integrate over the heavy quark mass. Then here you have a non-relativistic QCD, heavy quark effective theory. But now if you focus on the quarkonians, so they are kind of weakly bound states in median with a certain distance that is characterized by this so-called soft scale. Okay, so if you focus on even the low energy regions for quarkonians, you can integrate over the energy above these soft scales, and that gives you a sort of potential non-relativistic. So then here you still have the degrees of freedom of very single heavy quark, but here the degrees of freedom becomes like quark. Okay. And basically we want to combine this with the open quantum systems to get kinetic equations. Okay. Yeah. But anyway, yeah. So the idea is that basically the open quantum systems want to track the evolutions of this system density matrix. Okay. So basically this will be governed by the. You can actually have this. Schrodinger equations for the evolutions of density matrix. However, this is a unitary and time reversible equation. Nevertheless, if we focus on the systems, we can trace over the environment. Then this leads to the unitaries and the time reversibilities. Right? So we trace over the environment density matrix, and here we mostly focus on the QGB case. So this is more or less like a kind of a constant density matrix. It's like slow time varies temperature. Okay. So what we focus on is actually this density matrix system part. Okay, and then with the expansions of the HI, the interaction Newtonian, you can actually get this kind of perturbative expressions of this systems density matrix, and then these interaction terms are then related to the environment density. Environment operators encoded in these interactions as Hamiltonians. And in the end, this will be just the chromo-electromagnetic fields for our case. Okay. So I just skip this some details here. But the point is later how we can convert this kind of master equation or Schrödinger equations into the kinetic equations. And usually people consider the different kinds of limits. One is the so-called quantum optical limit, and one is the quantum Brownian motion limit. But today we will mostly focus on this limit. So this limit requires that the relaxation time scales, is much larger than the environment time scales, which is roughly one of the temperatures of plasmas. And also it requires the relaxation time scale to be much greater than the system time scale. And this is proportional to 1 over mv squared as basically the binding energy. So if you take this limit and then you do the Wigner transform of the master equations, you can get the Boltzmann equations of this Quarkonian's distributions. And you also have the interaction terms, basically like what I showed you. So also here, this relies on the coerced gradient that the so-called Markovian approximation is valid. So the time spacings for this kind of time derivative is between the relaxation time scales and the environment time scales. And from this, you can actually derive such a kind of kinetic equation. This F lambda is the distribution function of a vector Quarkonian. Okay, and so it comes from taking the Wigner transforms of the density matrix. But now notice that because this is Quarkonians, come from quark, antiquark, it's actually a kind of color matrix. Okay, not only the spin, but the color matrix. So you also have the so-called color uptake component. This is the color uptake distribution function. So the singlet corresponds to the real Quarkonian, but the uptake is like kind of loosely bound stages of these quark antiquark pairs in the quantum class. And lambda is because we consider the vector Quarkonians and also the diagonals as components of a density matrix. So we just have a 3 polarizations, it's 1, -1, 0. Okay. So the point is that the collision term, you have 2 kinds of contribution. One is the dissociation, right? So the dissociation term is governed by the color singlet distribution function, because you have basically the Quarkonians scatter with the gluons and then dissociate. Right? But for the recombination term is opposite. You have this loosely bound pair recombine due to also the scattering with the gluons and form the Quarkonians. So the effective field theory of this PNR QCDs is just give you some detailed information about how these 2 terms comes. Okay. Do some calculation and calculations. I will probably skip some part because I have enough time. So I will skip probably the PNR QCD. Yeah. But I just want to show the final result and some important points. So in the end, okay, after this very complicated calculations, you get the dissociation terms for the Quarkonian distribution function. The NLs are some quantum number, so you can actually also consider some excited states, not necessarily the ground state. But let's say just focus on ground state. We take n equal to 1 and 0. Now, basically, this complicated collision terms include the energy momentum conservation. So basically, the process is what we have is like this. For example, you have a jet side, which is scattered with the gluon, comes all the inverse process. So basically, you have some momentums of a jet side and this CC bar pair, Q bar pair, and then the energy of gluons. And this is the scattering amplitude squared, and this is the color singlet distribution function. It's a dissociation. And this amplitude is somewhat complicated. It's related to some wave functions of the quarkonia. So that have to be solved from this kind of wave equation with the potential. This is the static potential. So you could have basically you can consider just the Coulomb solutions. Yeah, but point is that now this terms contains two contributions. One comes from this color electric field correlator. So this is a correlation connected by the Wilson line at the joint Wilson line. So this V can be color electric field or color magnetic field. So the first term here, this is related to the two color electric fields correlator. And these directions are coupled to this dipole direction. So this dipole direction is actually random whole space. So basically, for this kind of a color electric field correlators contributions, this kind of collision term is actually spin polarization blind, unless you have some very special form of polarization independence of wave function. But basically, the chromo-electric field correlators give you kind of a spin polarization blind. And this kind of terms has already been derived previously without considering the spin point. But the difference is that now, if you consider the chromo-magnetic field contribution, but this kind of term will be 1 over n squared expressed. So in principle, in the systematic power content, this is like higher order correction. But such a term can lead to the polarization because this chromo field now are coupled to this polarization directions of the vector quarkonia. Okay, so basically, the new part derived in our paper is this new part where the color chromo-magnetic field correlators can give you the polarization dependent dissociations. Yeah. And this Wilson line will have to take some particular form. Such a case, this is a dissociation term. Similarly, you have the recombination term. Again, the chromo-magnetic field part is important, which actually gives you the polarization dependence. Not for the color electric correlator part. So basically, that's what we get in our papers. I mentioned something about some preliminary results that may be dangerous to be put on YouTube, but anyway, let's say, okay, if we really want to apply these formalisms to study the spin alignments for quarkonians, whether it's really reliable, especially if we want to really consider the glasma effect, that will be a little bit tricky because, as I mentioned, for this environment part, we basically consider the quark plasma constant constant density matrix or environment part. Right? So that's not the case in glasma because glasma evolved. However, we want to consider the scenario that if you just focus on this coalescence or the recombinations, these quark and antiquarks to form the quarkonians at the boundaries of the plasma. So that's just at the very short period, just before you enter the quark plasma. Then we may possibly neglect this kind of time dependencies. Okay. Right. So which means is we just, for this whole kinetic equation, we don't really track how they are produced in early time and evolve in plasma, but just focus on recombination at the final hours forms. And somehow yeah, for the scale separations, there exists some subtle issue, because if you really input some typical values of this like MV squares, etc., you realize that this one of these multiple expansions that we introduce with the assumption of the small separation of these quark and antiquarks does not really work as well as for the depth side. For Charmonian, it's a little bit difficult. But for Bartolommean, this distance is smaller, then this kind of expansion may still roughly work. So here, what we consider anyway is the cases for let's say Bartolommean cell with saturation scale is around 1 GeV. It's too high, also it does not work. So the interesting part is that I forgot about Markov approximation. The interesting part is that in such a case, because also for Upsilon, the advantage is that Upsilon is quite heavy. So this chromo-magnetic fields in the QGP contributions will be suppressed. Right? So it means that if you have this Bartolommeans that enter the QGP phase, most of the dissociation recombination just come from the chromo-electric correlator, and that is spin blind. So the only spin polarization information will be just encoded in these recombinations at the glasma phase. And also because in the glasma phase, we have this anisotropic of these chromo fields. And this is actually the major source that lead to the polarization, because in such a case, these polarizations will be, the projections will be only along the z direction. So this turns the important one that gives you the polarizations. And so in such a naive scenarios, what you get is that these deviations of a low 0, 0 from 1 is just governed by basically the chromo-magnetic field correlator turn to the chromo-electric field correlator turn, or the electric dipole turns. Okay. These two field correlators could be at the roughly the same values at the glasma phase. So these cancel each other. So what are related is actually these two scales, these softer scales and then the mass scale. And it turns out that you can read out, for example, MV square here for Bartolommean. Turns out this value is roughly 0. So this is a very, very simple order of magnitude estimate, but it shows that this value is already kind of sizable, because this is a very simple approximation. You can easily get a factor of 10 here, factor of 0.01. No, but it means that further study may be needed. This effect may not be really needed. Yes, that's basically our goal. That we got this preliminary result, and then we want to then further push it to have a more detailed calculations. Basically, that's the idea. So let me go to the summary outlook. So in general, spin alignment is maybe a useful tool for we call strong interaction force. It can be glasma field, this phi meson fluctuating fields, etc. That by basically gluons just matter, and the glasma and the QGP effects may be responsible for spin alignment in low and the mid transverse abundance. Okay, so they are more important than the different region. But again, yeah, the graph this estimate is subject to many approximations of phi. And in the end, I show you this spin alignment of quarkonia maybe started by this EFT plus open quantum system approach. Again, further study. Outlook, for the outlook, yeah, if you are interested data, yeah, we can talk privately. We are also considering, well, the local spin polarizations by color fields, not a global one, but the local one. And also you can ask if we can observe this spin alignment, large collision. How about a small collision system, but with the high multiplicity? like PA collisions at HC energies with high multiplicity bands, we could also possibly form the glasma. And we could possibly also study the spin alignments there. Yeah. And the experimentalists, are actually interested in that. They will probably. So far, there are just some studies about this, but mostly focused on the low multiplicity event because they need to take the dilute approximations. It's interesting that we see the high multiplicity happens. Thank you. Oh, by the way, finally, let me advertise. So in September, we will have the initial stage conference in Taipei. Yeah, so you guys you're all welcome to attend also. Unfortunately, the deadline for the submission of abstracts has passed, but the early bird registration is still available. Okay, yeah, thank you very much.